Hello everyone. I would like to lecture about multirate signal processing. Introduction to multirate signal processing. Multirate signal processing is a branch of digital signal processing in which signals are processed at multiple samplers within the same system. Instead of maintaining a fixed sampling frequency throughout the signal chain, multirate systems dynamically increases or decreases the sampling rate using upsamplers and downsamplers. This approach allows different parts of systems to operate at rates that best match their bandwidth requirements. As a result, multi-rate DSP provides both flexibility and efficiency, making it a fundamental concept in modern digital communication, audio, and multimedia systems. Importance of multi-rate signal processing. Importance of multi-rate signal processing is an ability to reduce unnecessary computation by performing signal processing tasks at the lowest possible sampling rate. Many DSP operations, especially filtering, becoming computationally expensive at high sampling rates. Multirate technique allows narrowband signals to be processed efficiently without sacrificing performance. This leads to reduced hardware complexity, lower power consumptions, and faster processing, which are critically requirement in real-time DSP systems. Here is the process how it's going to be in the multirate signal processing. This is the image. Sample rate conversions in DSP system. Sample rate conversion is required whenever a signal moves between systems operating at different sampling frequency. For example, digital audio devices, communication systems, and data converters often operate at incompatible rates. Sampling rate convergence ensures seamless interactions between such systems without loss of information. This process involves increasing the sampling rate through interpolation or decreasing it through decimation while preserving the original signal characteristics. Upsampling techniques. There are three upsampling techniques that are zero insertions, spectrum effects, interpolation methods. Upsampling is the process of increasing the sampling rate of discrete time signal by integer factor. This is achieved by inserting zero value samples between existing samples, which effectively reduces the sampling integral. Although the sampling increases the number of samples, it does not improve signal resolution by itself. Instead, it prepares the signal for further processing, such as interpolation filters, which reconstructs the intermediate sample values. Now let's go into deep. Zero insertion. Zero insertion is a process used in interpolation where zeros are inserted between successive samples of discrete time signal. It increases the sampling rate but creates spectral images, which are removed using an interpolation filter. And next, coming to spectrum filters, cause the original spectrum to be compressed by a factor L and produces repeated spectral images at multiple of original sampling frequencies. These unwanted images must be removed using an interpolation filter, that is a low pass filter. Next, coming to interpolation methods. Common interpolation methods include zero order hold or first order interpolation and ideal sign interpolation. In practical DSP systems, FIR low pass interpolation filters are used to remove spectral images and achieve accurate signal reconstruction. Next, interpolation filters. An interpolation filters such as filter characteristics, FIR implementations, spectrum images. Interpolation filters are designed to remove the spectral images produced during upsampling. These filters are technically low-pass filters that pass the original signal bandwidth while attenuating unwanted frequency components. FIR filters are commonly chosen because they are inherently stable and provide linear phase characteristics. Proper filter design ensures that the interpolated signal closely matches the original continuous time signals. Next, coming to downsampling. Downsampling reduces the sampling rate of a signal by an integer factor. This operation decreases the number of samples per second and reduces the amount of data that must be processed or stored, while downsampling improves efficiency. It reduces the risk of aliasing if high frequency components are present. Therefore, downsampling must always be combined with appropriate filtering to preserve signal integrity. There are three methods in this: retaining samples, signal spectrum, and anti-aliasing. Retaining samples refers to the process in downsampling where only every nth sample is kept and the remaining samples are discarded. Signal spectrum. The signal spectrum represents the frequency component present in signal and their corresponding amplitudes. It shows how the signal's energy is distributed over different frequencies. The next, anti-aliasing. Anti-aliasing is a process of low pass filtering a signal before downsampling to prevent overlapping of spectral components. It ensures that aliasing distortion is avoided when sampling rate is required. And decimation filters. There are three filters that are subdivided here: anti-aliasing, filter design, and computational constants. Decimation filters are specifically designed to prevent aliasing during downsampling. These filters must have a sharp cutoff and high stop band attenuation to effectively suppress unwanted frequency. FR filters are commonly used here due to their predictable behavior and stability. However, such filters can be computationally demanding. Such motivates the use of multirate optimization techniques. And understanding the noble identities in DSP system. Noble identities are mathematical properties that simplify multirate DSP system. They allow filters to be moved across unsamplers or downsamplers without changing the overall system response. The rearrangement enables filtering at a lower sampling rates, which significantly reduces the computational complexity. Noble identities play a key role in efficient DSP implementations. And this is the diagram of this one of this DSP systems where the signal is processed and sampled into, and there are some filters introduced here for upsampling and downsampling. Polyphase decomposition. Polyphase decomposition breaks a filter into multiple subfilters, each operating at different phase of input signal. This method avoids redundant computation, essentially those involving zero samples introducing during upsampling. By processing only the necessary samples, polyphase decomposition greatly improves efficiency and is widely used in practical multi-rate systems. Here, there are three subtopics here: filter representation, decimation systems, interpolation system. Filter representation expresses a digital filter using different frequency and transfer function or impulse response. It helps in analyzing and implementing filters efficiently in time and frequency domains. And next, coming to decimation systems. Decimation systems reduces the sampling rate by factor m by first low pass filters in signaling and then retaining every mth sample. The filter prevents aliasing, ensuring accurate signal representation and after downsampling. And next, interpolation systems. Interpolation systems increase the sampling rate by a factor L by inserting zeros between samples followed by low pass filters. And these are the three methods. Here I have shown you the diagrams of that one. Polyphase and decimation systems, interpolation systems, and the signal is processed in three different categories here. And next, polyphase structures. Polyphase structures implements filters using polyphase components to achieve efficient multi-rate passing. Compared to direct form realizations, these structures require fewer arithmetic operations and lower memory usage. As a result, polyphase structures are preferred in real-time DSP applications, where speed and power efficiency are critical. I have shown you a small comparison between polyphase structures versus direct form realizations. Polyphase structure decomposes the filter into subfilters that operate at lower sampling rate. This significantly reduces the number of multiplications and additions required. They avoid redundant computation caused by zero-valued samples in multi-rate systems. Direct form realizations performing filtering at the highest sampling rate. These result in higher computational complexity and power consumption. Hence, polyphase structures are more efficient and preferred in practical multi-rate DSP systems. Next, coming to multi-stage sampling rate conversions. Sampling conversions divides a large sampling rate change into several smaller stages. Each stage performs a simpler conversions which reduces the filter order and complexity. This approach improves computational efficiency, numerical stability, and implementation flexibility, making it deal for a larger conversions ratios. The sampling rate in multiple smaller steps instead of one larger step. The overall conversion factor is factored into cascaded stages of interpolation and or decimation. This approach reduces filter order, computational complexity, and memory requirements. Hence, multi-stage conversion is more efficient and practical for large sampling rates changes. Um, this is the diagram you have seen here. How the multi-rate sampling rate conversions explained in each subtopic and how this will be done in each process. Next, understanding filter banks in DSP system. Filter banks are systems that decompose a signal into multiple frequency subbands. Each subband represents a specific portion of signal spectrum and can be processed independently. This enables efficient signal analysis, compression, and feature extraction. Filter banks are fundamental to many modern signal processing techniques. Structure of quadrature mirror filter banks. Quadrature mirror filter banks are a special type of two-channel filter banks designed for efficient subband processing. The analysis filter the analysis filters split the signal into low and high frequency components which are then downsampled at this stage. At the signal stage, the signal is reconstructed using upsampling and filtering with aliasing effects cancelled through careful filter design. And applications of multi-rate signal processing. Multi-rate signal processing is widely used across many engineering fields in audio and speech signal processing. It enables efficient compression and resampling. In image and video processing, it supports multi-resolution analysis and compression standards. In communication systems, multi-rate techniques allows efficient channelization and bandwidth management. And these are the methods where we can use the multi-rate signal processing in a speech and communication devices and signal processing and some digital systems and some radios and how the signals is processed here by this process. Here we can see and the summary of multi-rate DCV systems. Multi-rate signal processing provides a powerful framework for efficient and flexible digital signal processing by using interpolation, decimation, polyphase structures, and filter banks. Multi-rate systems significantly reduce computational complexity while maintaining signal quality. These concepts from the foundation of many advanced DSP applications used today. Understanding the key benefits and techniques of multi-rate signal processing. Multi-rate signal processing enhances efficiency and flexibility in digital signal systems. By utilizing interpolation differentiation techniques, it significantly reduces the computational complexity while maintaining signal integrity. Polyphase structure feature streamline implementation, allowing for efficient management of resources and improved performance in various applications. Here we can see the how multi-rate signal processing is processed here. The signal is first passed into filter and next it is multi-rated and next it is sampled. Um, and this is a lecture of multi-rate signal processing and we got a somewhat clear view of multi-rate signal processing and how it's be done and what are the process in it and what are the equipments we use and what are the applications where we can use multi-rate signal processing. Many ways we can use multi-rate signal processing in digital systems, filters, and communication devices, and many other sectors we can use this multi-rate signal processing. And I got this multi-rate signal processing from the digital signal processing by Sadeku 4th edition. There is a brief view of how a signal is processed in multi-rate. You can go through that one if you want. And I have given a brief view of how a multi-rate signal processing is done in this lecture. Thank you.